Okay. So this is a continuation of our discussion of chapter 2, methods of integration. This will be under the proper integrals and a method of integrating rational functions, and we call it integration by partial fractions. This will be not last, but second to the last topic for chapter 2. We still have one more method, the rationalizing substitution, still under proper integrals. Last meeting we discussed this one, the uh, rational functions or polynomial in rational forms, and we define the improper and a proper rational functions. When we say uh, proper, the the degree of the uh, numerator is less than the degree of the denominator. So review natin. So if we have the degree of the numerator, so our functions uh, is in the form of this one. The numerator is a polynomial, and we have the denominator. It's also a polynomial. This is a function, a rational function. Then if the degree of this numerator is less than the degree of the denominator, then we call that a proper function, proper rational function. But if the degree of the numerator is greater than the degree of the denominator, then it's improper. Why do we need to know this one? Why do we need to identify if it's proper or improper? Because in applying integration by partial fractions, every proper rational functions can be expressed as a simpler fraction or partial fraction. So that's why we need to identify if that rational function is proper or improper. If it's improper, the numerator is greater than, we can still divide. Remember, if the numerator is greater than the denominator, the degree, we can divide, we can apply long division, we can apply synthetic division, and it will be in the form. We can still do this one before we apply integration by partial fraction. So it will be equal to the quotient. When we divide, then you just add if there's still a remainder in the division. So we can still uh, expand that rational function into this form. Then after that, this remainder will become a proper fraction or rational fraction. Then here we can now apply the partial fractions. And in applying partial fractions, there are different cases that we need to know. Depends on the problem that we will be dealing. These are the cases. So, case one. Case one is if denominator, the denominator contains distinct linear factors. If the denominator contains distinct linear factors, when we say linear, the degree is 1. And if we say distinct, it means the linear factor occurring once in the denominator. This will be case 1. If we see, this is in the form a all over ax plus b. So if you look at the denominator, then it's a linear factor. And here In case 1, we will be determining that A, constant E. And we will have example later on when we discuss all the different cases. So the partial fraction will be in this form, ax plus b. You just expand them. So for example, if you have 1 over x squared minus 4, this is the same as 1 over x minus 2 multiplied by x plus 2. So if you look at the factors, what are the factors? X minus 2 and x plus 2. So they are distinct. They appear once and they are linear. So what we do is we apply the partial fraction in the form a over x minus 2 then plus b minus x plus 2 and so on. So in general, if you have a numerator, then you have a factors ax plus b, you have cx plus d, and so on. Then this will be a over ax plus b plus c over, or b over cx plus d. So that's case 1. Then after that one, it's a simple partial fraction. You can integrate. After finding these values a, b, c, d, this constant, you can now apply integration. It will be easier to integrate because we have linear factors on the denominator, and that will be, if you apply substitution, basic substitution, let u equal to that denominator, and your differential or derivative will be just equal to dx, will be, and it will always appear on the problem, dx. You don't need any neutralizing factor if there's no coefficient for dx in the denominator. So that's case 1. Next, for case 2, how about if it's not distinct? It's a linear, but not distinct, meaning it appears more than once, or it is repeated. Repeated linear factors. Repeated linear factors. So what will we do if we have a repeated linear factors? So we will expand that into partial fraction in the form a over ax plus b plus, let's just call this one a1, this one a2 over ax plus b square plus dot 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 plus until it depends on how many times that factor appears in the denominator, ax plus b raised to n. So for example, if the factor or the denominator contains repeated roots. So if we have here, let's say 4x plus 2 whole over x minus 2 to the fourth. So if we apply case 2, this will be equal to a1 all over x minus 2 plus a2 all over x minus 2, and this will be squared, plus a3 over x minus 2, and this will be cube until a to the fourth all over x minus 2 to the fourth. And that's repeated linear factors, that's case 2. Then after that, from here again, if you look at our denominator x minus 2, you can apply substitution here, x minus 2, x minus 2, x minus 2. Even if it's cube or squared, you can still let it as your a u, and it will become more. For example, this square here, it will become 1 over u squared is 1 over u cube, and 1 over u to the fourth. And it's still a basic integration compared to integrating this the main problem, because in the main problem you have a 4x plus 2. You have remember these a's here, a1, a2, a3, a4, these are constant. They are just constant. There is no variable x appears in those values. Now, case 1 and case 2 is for linear factors. The next case will be if your denominator contains a distinct quadratic factors. This time it's quadratic. It's not linear. When we say quadratic, the degree is 2, second degree. And for this case 3, that quadratic factor should be irreducible. The irreducible. It means we cannot factor out that quadratic factors. So remember, when you apply this case 1, case 2, case 3, if you see quadratic factors in the denominator, don't assume that it's automatic, it's case 3 or case 4. Try to factor that out. Then if you can factor that out, it can still be reduced into a linear factors, and it will fall to either case 1 or case 2. So it will not be case 3. Case 3 is for irreducible quadratic factors, when the quadratic factor cannot be factored out. So this will be case 3 if it's distinct. Then what will we do? What will be the form for a quadratic factor? So for a quadratic factor, this will be in this form, plus ax squared plus bx plus c. So if it contains ax squared plus bx plus c, if this quadratic factor here in the denominator is reducible, then we can do this one. And for case 4, if it's repeated quadratic factors, still irreducible factors, quadratic factors, what will be the form? They corresponds in this form, a1x plus b1 all over ax squared plus bx plus c. It's almost the same with the case 2, but this time it's in quadratic. We just repeat case 3. a2x plus b2 all over ax squared plus bx plus c. And this will be squared. And if and so on, if it's raised to 4, then until 4, so until an x plus bn all over ax squared plus bx plus c raised to n. So this will be the form that we will be using if we encounter case 4, where a's and b's here are these are all constants. Now let's take an example. Evaluate this one, dx all over x squared minus 9. So what will be the case for example number 1? So because it's quadratic, it's a square, sir. This is a square. So this means the denominator is quadratic. So it means it's either case 3 or case 4 because it's quadratic. So is it case 3 or 4? Remember, again, it's not because the denominator is quadratic, you can automatically say that is case 3 or 4. Can we factor out the denominator x squared? X squared minus 9. What's the factor here? Remember your special product. This is the same. Your special product. A squared plus or minus b squared. This is the same as a plus b times a minus b. This is a special product. So in our case, this is x squared minus 9. But we can factor out this one into this form. So this will be x, what's the square root of 9? The square root of 9 is 3. X plus 3 times x minus 3. And if you look at now, this one, this is not case 3 or case 4. This falls under case 1. It's a distinct linear factors, x plus 3 and x minus 3. It's distinct. It's not repeated. So we can rewrite now the problem. This will be 1 over x squared minus 9. And we will apply the partial fraction. Where does this came from? It came from dx over x squared minus 9. I just removed the x, and I will go back to that problem later on after we apply partial fractions. And applying case 1, this will be a all over the first factor, x plus 3. Then plus b, the second factor, x minus 3. So we now applied the case 1. Or we can just remove this one. Or we can do this. X plus 3 and x minus 3. X plus 3 times x minus 3. So that's the first thing. The first step is to factor out the denominator as much as possible. Then after this one, we need to find a and b. So how do we determine a and b? There are two methods in determining a and b. The first one is by setting s to 0 and solving the other constant. And the second method is by equating the coefficients of x. So we can do both, but for this type of problem, it's easier to use the substitution. We substitute values for s. And to do that, for x, to do that, we first multiply both sides of this equation by x plus 3 times x minus 3. So this will be 1 equals a times we distribute this one, x plus 3 will cancel out. So this will be times x minus 3. Then plus here we have b times x plus 3. X minus 3 will cancel out. Then from here, we will assign value for x. So to assign values, to choose the value for x, we need to make sure the constant will become 0 or will cancel out so that we can solve the other constant. So for example, here, if I want to solve for a, I must eliminate the second part here. So what should be the value of x so that this part will become 0? So we can use x, let x be equal to negative 3. Why negative 3? Because negative 3 plus 3, it will become 0. So if we multiply it with b, and this term will be equal to 0. So applying that, 1 equals A times negative 3 minus 3 plus B times negative 3 plus 3. So this will become 0. And negative 3 minus 3 will be negative 6. So this will be negative 6A. Then solving for A, that will be A will be equal to negative 1 over 6. Then for constant B, that will be the value for x. We can choose 3. Then this will be 1 equals A times 3 minus 3 plus B times 3 plus 3. And that will be the value for B. So this will be 0. This will be 6. So B will be equal to 1 over A equals negative 1 over 6, and B is equal to positive 1 over 6. Then we can now substitute these values in the problem. Or we can use the other method also if you want the other method, the equate coefficients. Equating the coefficients of x. Why do we need two methods? Because this first method here, what we did here is we choose values for x, but there are some problems that whatever value of x you put, the other coefficient or the other constant ABCs will not cancel out. So you cannot find any value for x that will cancel or will make the other constant 0. So if you cannot think of values for x, then the other method will be this one. You equate the coefficients. This is the last resort if you cannot find AB using the first method. But if you can find the constant using the first method, then you don't need to use this second method. So equate the coefficients or the powers of x. Then after that, we will solve it simultaneously. So for the first one, you have our equation 1. Let's just rewrite this one. A times x minus 3, then plus b times x plus 3. X plus 3. Then the next step is to distribute. So we distribute ax minus 3a plus bx plus 3 times b. Then we factor out all the terms that has x. So we have a, then we have plus b, then x, and we have minus, or we can also factor out 3 here. 3 times b minus a. b minus a. Then we equate the coefficients. What are the coefficients for the left side of the equation? All the coefficients of terms that contains x raised to 1, or simply x, because this is the highest degree here, x raised to 1. So at the left side, we don't have x at the left side, so this will be equal to 0. That's now x. While at the right side, this is x here, and the coefficient of x is a plus b. So this will be a plus b. So that's equating coefficients. We equate the coefficients at the left side to the coefficient at the right side. So this is by inspection. We inspect the equation. Then next, for x raised to 0, what is x raised to 0? X raised to 0 is a constant. X raised to 0 is 1. On the left side, we have a constant here, a constant 1. So that will be the coefficient of x raised to 0. Then at the right side, remember a and b is a constant. So this also should be equal to 3 times b minus a. Because that's the constant of the right side. Then after that, we can now solve these two equations simultaneously. So from the first equation here, we can derive a is equal to negative b. We put b at the other side, it will become negative. Then after that, we substitute that equation here. So this will be 1 equals 3 times b minus what is a? A is negative b. So minus a is negative b. So this will be plus b. Then we can now solve for b. This will be 1 equals 3 times b plus b is 2b. Then we multiply 2 times 3, this will be 1 equals 6 times b. Then solving for b now will be equal to 1 over 6. So if we check with our previous method, b is equal to 1 over 6. They're the same. And for a is equal to negative of b. And b is 1/6. So therefore, a is just equal to negative 1 over 6. This is the same again with the first method, negative 1 over 6. So that's the second method of solving the coefficients by equating. The first one is by substituting. Then we go back to the problem. This one now, dx over x squared minus 9. We can rewrite this one as, so the integral of dx over x squared minus 9 now will be equal to the integral. So what's the partial fraction? A over this one, a over x plus 3 plus b all over x minus 3. So a over x plus 3. Our a is negative 1 over 6. And this should be all over x plus 3. Then plus, the other one is b, which is 1/6, all over x minus 3. Then I just factor out that dx. And this part now will be, this is 1 over x squared minus 9 when we do the partial fraction. And we can now integrate this. So we can distribute the integral. So this will be the integral of 1 over 6 dx over x minus 3, then minus 1 over 6, the integral of dx over x plus 3. Now, how do you integrate this one? Let u be equal to x minus 3. Let u be equal to x plus 3. What will be your du? Our du will be dx. Our du here will also be dx. So what will be the form? It will be du over u. Du over u. So what's the integral of du over u? It's just ln of u. So the answer now, directly we can answer this one. I don't need to put the substitution. This will be equal to 1 over 6. ln of u, ln of x minus 3, minus 1 over 6, ln of u, x plus 3, plus c. This is now the integral of dx over x squared plus, or x squared minus 9. For next example, let's take this one. Example number 2. Evaluate the integral of x plus 2 all over x cubed minus x squared minus 2x dx. So the denominator is in third degree cube. So wala ito sa case natin. but we can still factor out this one. So the first step is to factor out the denominator of the solution. X cubed minus x squared minus 2x. So we can factor out first yung x. So this will be x squared minus x minus 2. Then this quadratic here, is it irreducible? We can still factor these out. So what's the factor of this quadratic expression? X factors of 2, 2, and 1. When you add, it's equal to negative 1. So this should be negative 2 and plus 1. So we can reduce the denominator into this form. So this will be x plus 2 all over x times x minus 2 times x plus 1. Then what will be the case under this example? It's still case number 1 because it's linear factors and none is repeated, or they are all distinct factors. So to evaluate this one, to apply partial fraction a over x, then plus b over x minus 2 plus c all over x plus 1. Then next step is to determine the values for a, b, and c. There are two methods. We will be using the first method, the substitution. So the first step is to multiply both sides with the denominator x times x minus 2 times x plus 1. So this will be x plus 2 equals a, cancel out yung x. So x minus 2 times x plus 1. And we have b times x. X minus 2 will cancel out, so this will be x plus 1. Then for c, x plus 1 will cancel, so this c x times x minus 2. This is x plus 2. Then applying the first method in determining the coefficients or determining the constant ABC. So what value of x should we use first? So we can solve for a first here. So to cancel out or to make these two terms 0, we can let x to be equal to 0. So this will be 0 plus 2 equals a times 0 minus 2 times 0 plus 1 plus b times 0 plus 1 plus c times 0 minus 2. Then 0 plus 1, 1 times 0, this will become 0, and this is also 0. So we have here 2 equals negative 2 plus 1. So this will be negative 2 times 1 is negative 2, so negative 2a. So our a will be equal to a negative 1. The next, how about for b? What should be the value of x for us to solve for b? So b here, we want to cancel this one and this one. So we can let x be equal to 2 because they are both have x minus 2. So this will be 2 plus 2 equals a times 2 minus 2 times 2 plus 1 plus b times 2 plus 1 plus c times 2 minus 2. And this will be 0 and this will be 0. So the remaining will be 2 plus 2 is 4. And this one, 2 plus 1 is 3 times 2. So it's 6 times b. So b now will be equal to 4 over 6. Or this is 2 over 3. Okay, then next for the last one for c, we can make x to be equal to negative 1. Negative 1. So we have negative 1 plus 2. Negative 1 plus 2 equals a times negative 1 minus 2 times negative 1 minus plus 1. Then plus b times negative 1 times negative 1 plus 1, then plus c times negative 1 times negative 1 minus 2. And this will be 0 and this will be 0. Solving for c, negative 1 plus 2 is positive 1. And this is negative 1. Negative 1 minus 2 is negative 3 times negative 1. It's positive 3 times c. Then solving for c, c now will be equal to positive 1 over 3. Then we have now the x plus 2 all over x cubed minus x squared minus 2x now will be the same as a over x, or a is negative 1. So we have negative 1 over x, then plus b over x minus 2. Our b is 2/3. 2/3 over x minus 2. Then for x plus 1, c is 1/3. So this is 1/3 x plus 1. So this is now the partial fraction of that given. So we can now integrate this one instead of this one. So the integral of negative 1 over x plus 2/3 over 2/3 over x minus 2 plus 1/3 over x plus 1 dx. Distribute the integral, so this will be negative the integral of dx over x plus 2 over 3 the integral of dx over x minus 2, then plus 1 over 3 the integral of dx over x plus 1. And we can now solve this one. So the integral of x plus 2 all over x cubed minus x squared minus 2x dx now will be equal to integral of dx over x is ln. So this is negative ln of x. Negative ln of x plus 2/3 ln of x minus 2 plus 1/3 ln of x plus 1 plus c. So that is the integral of x plus 2 over x cubed minus x squared minus 2x. Still under case 1. Now, how about case 2? Example for case 2. Let's evaluate this one. Integral of 3x plus 5 all over x cubed minus x squared minus x plus 1 dx. So first step, solution, we need to factor out the denominator, x plus 1. What's the factor? How can we factor this one? We can factor out this to be x plus 1 times x minus 1 squared, so that it will be equal to x squared plus minus x plus 1. So if you're not sure with the factor, you can expand this one to check if it's true. Then now we can apply the partial fraction, 3x plus 5 all over x plus 1 times x minus 1 squared. The first part, yung a over x plus 1, that's okay, that's case 1. But x minus 1 squared, this is case 2. This is case 2, this is repeated roots. X minus 1 times x minus 1, or x minus 1 squared. So if we apply case 2, the form will be plus b over x minus 1, then another plus c over x minus 1 squared. If it's raised to cube, then you need to add another 1 plus the x minus 1 cube, and so on. That's case 2. Then again, this is 3x, multiplying both sides by x plus 1 times x minus 1 squared, x plus 5 equals a cancel out x plus 1. So this will be x minus 1 squared plus b times, we can cancel out the x minus 1. So this will be x plus 1. Then there is still 1 remaining, x minus 1. And for c plus c, x minus 1 squared will cancel out. So this will be c times x plus 1. Then again, we use the first method to determine the values for a, b, and c. So let x be equal to, we can use -1. Let x be equal to -1. So this is 3 times -1 plus 5 equals a times -1 minus 1 squared plus b times -1 plus 1 times -1 minus 1 plus c times -1 minus or plus 1. We choose -1 because we want to solve for a. So b and c here will cancel out because it contains terms x plus 1. So if x is negative, then that will be equal to 0. So this will be 0 and this will be 0. 3 times -1, 3 plus 5. So this is positive 2 equals -1 minus 1, -2 squared. It's 4. So this is 4a. A will be equal to 2 over 4, or that is 1/2. Then for b, if we want to solve for b, we can let x be equal to bx plus 1. There's no x plus 1 in a. So we first solve for c before we go to b. We can use positive 1 as our x. So this will be 3 times 1 plus 5 equals a times 1 minus 1 squared plus b times 1 plus 1, 1 minus 1 plus c times 1 plus 1. So this will be 0 and this will be 0. So 5 plus 3 will be 8 and this will be 2. 1 plus 1 is 2, c. Then solve for c. C will be equal to 8 over 2 and that is 4. And to solve for b, to determine the remaining constant, we can use the other values that we already solved. For example, yung a, we can use 1/2 to substitute. And you can use any value for x. But the easiest here will be to use 0, so that it will be easier for us to simplify the equation. So the 3 times 0, so this is 5 equals a is 1/2. A is 1/2. Then 0 minus 1, so this is -1 squared, plus b times 0 plus 1, so that's 1. Then 0 minus 1, that's -1. Then c, we already know c is 4. 4 times 0 plus 1. Then we can solve for b. So b here will be -1 squared is 1/2. And we have 4. Then b will be equal to -1/2. Thus, this one now, 3x plus 5 all over x plus 1, or we can use that on 3x plus 5. So the integral of 3x plus 5 all over x cubed minus x squared minus x plus 1, the x is now equal to a over x plus 1. Our a is 1/2, so 1/2 over x plus 1. So the integral of 1/2 x plus 1. Then plus b over x minus 1. B over x minus 1. Our b is -1/2, so this is -1/2. 1 half over x minus 1. Then for the last part, c is 4, so 4 over x minus 1 squared. 4 over x minus 1 square. And this is dx. Then distribute the integral, so this will be 1 half the integral of dx over x plus 1 minus 1 half the integral of dx over x minus 1, then plus 4 the integral of dx over x minus 1 square. Then solve this one. Now, the final answer will be the integral of 3x plus 5 over x cubed minus x squared minus x plus 1 dx will be equal to 1 half ln of x plus 1, your u is x plus 1, minus 1 half x minus 1. Then, or this is ln. For the last part, this is du over u squared. So if it's du over u squared, what will be the integral of that? Du over u squared. What's the integral of du over u squared? So we can put u squared at the top, u raised to negative 2 du, and apply power rule. U negative 2 plus 1 all over negative 2 plus 1. C. Or this is u raised to negative 1 all over negative 1. Or this is negative 1 over u. So the answer here will be last or minus because it's negative. The integral is negative. It should be minus 1 over u. But we have still 4. So minus 4 over minus 4 all over u, which is x minus 1 raised to 1 over u, then plus c. And this will be the integral of this one. You can still simplify this if you want to simplify further. How do we simplify this one? The first two term, 1 half ln x plus 1 minus 1 half ln x minus 1. It's minus. You can just make it a division. 1 half ln x plus 1 all over x minus 1.